Okay, welcome to the first afternoon session of AbGradCon 2016. My name is Tessa Fisher. I'm a PhD student at Arizona State University, and I will be doing the warm-up talks for the origin of life and theory and computation sessions, and then also chairing half of the theory and computation session before I have to scurry away to the airport to go to another conference. So anyways, without further ado, so the fundamental questions we're going to be tackling this afternoon are basically, there we go. What is life, and how do we get from non-life to life? How do we go from inanimate matter to something that we can all more or less agree is a living organism? Admittedly, what exactly a living organism is also up to debate, which we'll get into. So for this afternoon, anyways, there's at least two major approaches we're going to be looking at. One is based off of prebiotic chemistry, which is sort of the some of the stuff that we saw earlier today as well, and then also information theory. So for the first approach I'll be talking about is going to be prebiotic chemistry, because that's a little more concrete. It doesn't get quite as mathematical and nebulous. And that's, at its core, is basically the idea of saying, okay, how do we go from these elements, carbon, hydrogen, oxygen, nitrogen, sulfur, and phosphorus, plus some trace elements, to simple organic compounds, and then from that to living systems, sometimes referred to as abiogenesis. And sort of the classic experiment for prebiotic chemistry is the Millerurey experiment, which I'm sure most of you have heard of. But if you haven't or need a refresher, the basic idea is that you create this glass apparatus, fill it with a series of reducing gases, methane, ammonia, water vapor, and hydrogen, and then run it through a system which heats it, cools it, subjects it to electrical discharge, which is supposed to simulate lightning strikes. The whole idea is basically you're simulating an early Earth environment of heating and cooling and changes in weather and tides and all stuff like that. And the cool thing about this is if you let it run for 24 hours or so, at the end you get down here this nice mucky collection of organic brown goo, chock full of organic molecules. Now, the problem with this, as it turns out, and this was a major breakthrough when it was discovered, but is less so now, is that we now have reason to believe that the atmosphere of the early Earth actually didn't look much like this. It was probably more nitrogen and carbon dioxide, not reducing compounds like methane and ammonia. So obviously, we're going to have to rethink how prebiotic chemistry works, because the nice thing about a reducing environment is that it does lend itself very well for the production of organic molecules. So we got to look at specific niches instead of trying to assume that it's just sort of this vast primordial soup everywhere on the planet. And there have been a lot of different environments that have been suggested for this. First one, hydrothermal vents. If you have very reducing conditions to the methane and hydrogen sulfide emitted, you've got very strong temperature gradients between hot and cold, from overboiling to near freezing. And you also get a lot of interesting geochemistry that happens here, which will give you a good feedstock to build molecules. And you also, we'll get later, they also get some interesting gradients that can set up as well. Another one that's been talked about is ice. Ice is really good at concentrating things, because as water freezes, the impurities tend to be the last things that freeze, and therefore you get them in little pockets. So that's really good for if you want to force reactions that ordinarily wouldn't occur by simply increasing the concentration so much that they suddenly become thermodynamically favorable. Clay crystals and molecules have also been suggested as a potential matrix or lattice for the formation of organic molecules. They also have some nifty self-replicating properties, which have been given some interest. And then my personal favorite, the radioactive peach, and this is a newer theory that came out a year or two ago, which is the idea is that the early Earth would have been much more volcanically active and much richer in radioactive elements, since most of them have decayed between now and then. And therefore, all these radioactive sediments would have gotten concentrated at the high water line of the beaches of planet Earth, and you would have had essentially this very energetic zone where all sorts of really weird radiochemistry would be going on. Don't know how likely it is, but I thought it was really cool. So, okay, we've got places where we can make really nifty organic compounds. Now what? Well, like I said, we don't exactly have a great definition or agreed upon definition anyways, for what a living organism is. But we do have a fair number of traits that most people can agree most living organisms, so far as we know, have. Replication, metabolism, and compartmentalization. And there is a bit of a debate in the origin of life and prebiotic chemistry community about which came first. For replication, you have compounds called autocatalysts, which are essentially chemical compounds that can catalyze their own formation, essentially replicate themselves in a very simple manner. One autocatalyst of particular interest is RNA, which is still used in our biochemistry to this day, but has the nifty feature of essentially being able to synthesize more of itself. So essentially, it's very easy for it to self-replicate. And it's strongly suspected that was probably the forerunner for the more stable and harder to replicate DNA that we currently use. Although, however, it's also been argued that from an evolutionary point of view, just being able, an RNA molecule that can turn out more RNA molecules may not exactly be advantageous if you don't actually hook it up to something like, say, metabolism. Which brings us to the next part. So metabolism is basically being able to take energy in your environment in one form or another and using it to synthesize more compounds or replicate or whatever. And there are people who believe that metabolism actually came first. One that I always thought was particularly cool, and some of the people in this room have actually worked on it, was, like I mentioned, at vents, you can have these really interesting gradients that set up. And in particular, in some cases, depending on how acidic or basic the vent fluid is, you can end up getting these weird electrochemical or ionic gradients, which are of real interest if you have background in biology, because pretty much all living organisms on the planet are ultimately powered by these sorts of electrochemical gradients, protein pumps and whatnot. So it's kind of like, well, maybe this is where that started, that you had these naturally occurring gradients that molecules learned, for lack of a better term, how to harvest and use that as sort of a way to power the construction of more and more elaborate molecules and eventually ones that were capable of self-replication. And lastly, compartmentalization. Obviously, a major part of being a living organism is being able to separate you from the rest of the world, or at least being able to control what comes in from your environment into you and what goes out. Otherwise, you just kind of end up dissolving into this mess. Now, the useful thing about the neat thing about compartmentalization is that it's actually pretty easy to set up. There are a lot of organic compounds, proteins, for example, that in aqueous conditions will kind of naturally just roll up into nice little spheres. So this one isn't quite as challenging as some of the other ones. Now, of course, there's no reason these all have to be mutually exclusive. It's quite likely that they probably all happened more about the same time or in very close proximity to each other. But still, they all had to have happened for us to get here. So that's kind of like where the baseline starting point for, okay, we're now officially a living organism. Which brings us to the next point of, okay, how do we define what a living organism is anyways? And for this, we're going to get a bit more abstract. So the one technique that's getting more and more popular is using sort of an approach that's based off of information theory. And it examines life and evolution at a more abstract level, mathematically. But the advantage of that is that it allows us to quantify the emergence and evolution of life. Since it's all done mathematically on computers, you can actually get specific figures and data as it goes through. And what is of particular interest to scientists who study this are complexity and emergence. Complexity is essentially where a system is, the sum is greater than the whole of its parts. The subcomponents of the system do not have the same properties as the system as a whole. Emergence, on the other hand, is the tendency for, in some systems, for very simple rules to give rise to very complex behavior and phenomena. A classic example is schooling fish. None of these fish are leading the other fish. They are all reacting to the same basic stimuli: proximity to each other, proximity to predators, proximity to food, and they're all independently deciding where to move. However, when you put them together, essentially all those small decisions add up to a much larger decision that is able to exhibit this really cool synchronized behavior and predator avoidance. So that gives you an idea. And emergence shows up all the times in biology. You have it in ant hives or ant nests and other social insects, in gene regulatory networks, in cells, and more than likely in consciousness, being the emergent property of how the neurons in our brain are wired, although that's still debated. That's a whole other conference. Another cool way to study these, and I know there'll be at least one talk this afternoon we'll discuss it, is cellular automata, which, again, looking at systems that can become emergent, is these very deterministic binary systems that use simple, discrete rules and can be used sort of as a toy model for life. They aren't obviously quite as complex as living organisms, but they have some of the same properties. Classic example of them is Conway's Game of Life, which some of you may have heard of. It's pretty simple. You have a grid of squares. Very simple rules determine whether or not a particular square is black or white, usually based on its proximity to other squares, depending if they're black or white. And while the rule set is very simple, you can fit on the page, you can get this really, really complex and interesting phenomena and self-replication, self-sustaining, and just all sorts of really cool stable and metastable states. And as a result, from these very simple rules, you have a great platform to sort of mathematically analyze evolution, emergent behavior, and also phase transitions. When you go from a very different regime, for example, one where you're not getting a whole lot of complexity, to one where all of a sudden there's an explosion of complexity, which, like I said, will be discussed in one of our later talks. And a lot of this, like I said, is grounded in information theory, and the idea that life itself can be defined as an information theory, or information process, rather. Now, information theorists love appropriating other sciences' words and giving them new definitions. So, for the purposes of an information scientist, information specifically refers to a reduction in uncertainty about the state of a particular component in a system. Transfer entropy, for example, refers to if you have two subcomponents of a system, how knowing the state of one subcomponent reduces the uncertainty of knowing the state of the other subcomponent if you had to predict it. So that's basically how much are they sharing information or how much is information flowing between them. Active information is kind of the same idea, except it's temporally. It's essentially a fancier term for memory. If you know the past state of a system, how much does that reduce the uncertainty for being able to predict the future state or current state of that particular system? Another tool in our toolbox, graph theory networks. This was discussed earlier. Graphs, when we talk about graphs, we don't mean pie charts. We mean these sorts of network designs where you have a node, which is just any particular system component, and edges, which are connections between nodes. And these are really cool for examining the interactions within a system. And different networks have different structures and motifs, which I'll get to, and they have different patterns of flow of information, and doing this allows you to track that and analyze it. For example, you have very centralized networks where everything's radiating off a central spoke. You have decentralized networks where there's a couple of very centralized spokes, but they're all connected to each other. Airports, the wheel and spoke model for airports, for example, is a classic example of that, where you have a couple of hubs and then a whole bunch of outlying airports that are in smaller areas. And then distributed where everything's kind of connected with everything else. Now, you can do some really cool stuff with this for astrobiology. You can analyze gene regulatory networks this way. You can analyze social insects. You can analyze metabolic interactions in microbial or just general biological communities, and also the chemical reaction networks of planets. To give you an idea, this is sort of a plug for what I'm probably going to end up doing for my dissertation. So you have these chemical reaction networks for an atmosphere, where you have all these reactions and then put into a sort of graph form. So this is the graph for the atmosphere of Mars. This is the graph for the atmosphere of Earth. And all the other planets in the solar system look like this, except for Earth. So something interesting is going on here. We don't know what yet. I'll probably be presenting on that next year. But just to give you an idea of what this stuff is capable of, it's pretty cool. So any questions? We've got time for probably one or two.